My name is Jay Baker. I'll be presenting for the yellow team spray booth pressure station. I'm one of three. The other two members are Joel Wood and Jamie West. This is an overview of the schematic of the system, the results of steady-state operating curve, the results of the step function, the FOPDT theory, the model theory, and FOPDT results, and some conclusions. This is the schematic of our system. We have an electric motor that uses a fan at the end of the output shaft, which produces a pressure with air pressure to go to three different booths that are used for painting, and the air is used for filtration. And we have three different filters on our system. We have a pressure sensor that relays back information of the centimeters of H2O of the pressure to our computer, so we get to collect the compiled data. This is a plot diagram or a block diagram of the way our system functions. The input of motor power percentage, which goes into the electric motor and fan apparatus, which is our system. And our output is in pressure in centimeters of H2O. This is a pressure versus time at 85% input power. This was used in the beginning of our constant input values, and we were able to find a steady state of 49 plus or minus 0.6 centimeters of H2O over a duration of 15 seconds. This is our steady state operating curve. It is split up in between the three of us. Jamie West is 5 to 30% input. I'm at 35 to 55% input, and Joel is at 60 to 85% output. This is a step up function in the range of 15 to 30 centimeters of H2O output. We ended up calculating delta M at 20 and delta C at 15. T naught was 0.1 seconds, and our tau was 1.5. All this information gathered together, we were able to find a K value of 0.75 centimeters of H2O. This is one of our step-down functions. It was from the range of 30 down to 15% centimeters of H2O. The delta M was the same at 20, but our delta C was at 14.8, which ended up giving us a K value of 0.74 centimeters of H2O. These are the slides that you didn't want me to use, so we'll skip over those. This is the FOPDT modeling equation. Using this equation, we input our data, and we had a parameter of TD equals 15 seconds, A is 20%, a K value of 0.75 centimeters of H2O per percent power, a T naught of 0.4 seconds, and a tau of 1.5 seconds. We used an input base load of 45% power and output base load of 15 centimeters of H2O. With this data, we were able to form a step-up range, a step-up function in the range of 15 to 30% centimeters of H2O. The K value that we ended up with on this range was 0.76 plus or minus 0.02 centimeters of H2O per percent power. The tau ended up being 1.5% plus or minus 0.3 seconds, and T naught was 0.1 seconds. This is a step down in the same range, going down from 30 to 15%, or 30 to 15 centimeters of H2O. We had a T naught of 0.1, which is the same as the step up, a K value of 0.74 plus or minus 0.15 centimeters of H2O per percent power, and a tau of 2.1 plus or minus 0.2 seconds. We have an overlay of our experimental data and our modeling inputs. The lines here are for input data, and the line here is for our output data. We use the model to correlate to our experiment data, and we're able to define that it was within the range of our model. These are our T-naught values, 1 to 15 centimeters of H2O, 15 to 30 centimeters of H2O, and 30 to 45%, 30 to 45 centimeters of H2O. We were consistent within the range, the upper and middle range, but we did have one deviation in the lower range, and we think it's due to system functionality. It performs within the mid to high range and doesn't have the capabilities of reading the actual inputs and output on the lower end. Our tau values for the same three ranges. We ended up the K values that we have for 1 to 15 centimeters of H2O, we're in the range of 0.4 centimeters of H2O per percent power, and 15 to 30 centimeters of H2O per percent power were 0.74 to 75, and that is where the error values on the error bars come into play. There's about 0.1. 30 to 45 centimeters of H2O per percent power, we had about 0.85 up to 1, and that is where the error comes in, just like 0.4. Experimental increasing step function data ended up with a steady state of a gain of 0.76 plus or minus 0.02 centimeters of H2O. Our dead time, whether going up or down, always ended up being 0.1 seconds. And our tau was 1.5 plus or minus 0.3 seconds. On the step up, we ended up with 0.75 centimeters of H2O per percent power, a dead time of 0.4 seconds, and a tau of 1.5. Some conclusions are we were able to understand our operating ranges and predict outputs. Our full operating range was 5 to 45 centimeters of H2O. On the FOPDT, the transfer functions are important for approximation and response to dynamic processes. We were able to use that to model our graphs and do experimental graphs to show the consistency. On the pressure system, we had a quick response time of 0.1 seconds on our T-naught, and we did have a differential in our tau. On the step up, it was 1.5, and on the step down, it was 2.1, which showed that it had a delay in its response. Any questions?